In this lesson, we are going to look at how you use the heat equation to solve problems for changes of state. Now you know Q equals Cm delta T, but there's actually one other equation that I need to share with you in this lesson. Some of the slides here are pretty large, so I have not included my video in this lesson, so you'll just listen to my voice. Let's get started. Now, when phase changes happen, you're going from a solid to a liquid to a gas maybe, or possibly with sublimation, a solid directly to a gas. Before you begin this lesson, I want you to review the characteristics of all three phases of matter. Look at the shape that each phase takes, look at the volume, if it's definite or if it changes. These are ideas that we studied very early in the chemistry course. Now when you're finished with that, I want to add one new idea. Entropy. Entropy is the amount of disorder in a system. So if you think about those characteristics of the atoms in a solid, a liquid, and a gas, solids are the most ordered state. Their molecules are close together and they're packed in an ordered arrangement. So solids have low entropy. Liquids have a little more disorder, more entropy, because as you know, their molecules are not in as much of an ordered arrangement as a solid. And then finally, gases have higher entropy because they have no arrangement to the molecules. They simply move around in random motion. Let me have you take a look at this website from Harcourt School to review those phases. While you're looking at them, think about the disorder and the entropy of each one of the samples. Okay, so here we have a sample of a purple looking solid. Okay, let's look at the solid molecules close up. They are moving, but they're in a very regular arrangement. Now if you raise the temperature a little bit, we can melt this purple solid. You see here that there's a little bit looser arrangement. Some of the particles are moving around pretty freely, others are just kind of wiggling in place, but the structure has broken down. And then finally, if we boil our liquid, we get a lot of space between the particles and a definite random arrangement. So the entropy is increased from one state to the next. Alright, now this slide's got a lot of information on it, but again, it's more review. Let's look at the names of the phase changes from one phase to another. Now I'll just start on the first line. As we go from a solid to a liquid, that's the phase change melting. We know that heat has to be put into the system for melting to occur. Think about ice turning into water. So it's an endothermic process, and the entropy of this system is increasing because we're going from an ordered solid to a less ordered liquid. In the second row, from a liquid to a solid, this is the opposite of melting, or freezing. If melting was endothermic, freezing is exothermic. We have to remove heat from liquid to make it a solid. And if it's an exothermic process and we're removing heat, the entropy is going to decrease. The disorder will become less. The third phase changes from a liquid to a gas. This is evaporation. That's an endothermic process. Endothermic processes add energy, so the molecules have more energy, they move around more rapidly and more randomly, so the entropy will increase. From a gas to a liquid, the opposite process is condensation. Remember, if evaporation was endothermic, condensation will be exothermic. They're opposites, so the entropy here decreases. And finally, those processes that are more unusual, from a solid to a gas, is sublimation. We have to add energy to make this process happen, so it's endothermic, and if we're adding energy to those molecules, they're going to become more disordered, so entropy increases. And then deposition finally is the opposite of sublimation, so the amount of energy The movement of energy is exothermic, it's the opposite of sublimation, and the entropy decreases because we're going from a gas to a solid. Now here's a heating curve that shows phase changes. I want you to notice that on the x-axis is the amount of heat added, that's going to be measured in joules, and on the y-axis is the temperature. You can see there are 5 distinct segments to this graph. There are slanted segments where the temperature is going up, and there are flat segments where the temperature is staying the same. Let me show you what each one of the segments means. This is the same diagram for water, but it's labeled, so I like to use this one when I'm explaining it. In the first slanted section on the bottom, we are at a temperature of negative 30 degrees. It's below the freezing point of water. So we have ice. And as we add energy to that ice, the temperature warms up until you get to 0. That's the melting point of ice. And then the temperature levels off. You have an ice-water mixture at that point. Now why does that temperature level off? Well, you know you're adding heat to the sample, so why does the heat not change the temperature? Well, what's happening is that the intermolecular forces that are holding the ice structure together are starting to be challenged. The heat that you're adding to that ice is causing the intermolecular forces to weaken. Some of the ice will melt into water. So the way I think about it is that the heat being added is being used to change the phase or the state of the ice, not to raise its temperature. Now when all of the ice is melted at 0 degrees, the temperature will start to rise again, and that's the slanted segment in the middle of this graph where you only have water. The temperature will rise until you get to 100 degrees. As you continue to add heat, the water begins to boil at 100 degrees. And you see the same type of temperature effect. At the boiling point, it levels off. The temperature stays 100 degrees until all of the water has evaporated. While you're at 100 degrees, you have a mixture of water and steam. And as you continue to add heat, the heat is being used to, again, weaken the intermolecular forces. It's being used to change the state of the water and turn it into a gas. When you have only steam, at 100 degrees, the temperature will rise again. And at that point, you get the last slanted segment of the graph. So remember that the slanted segments are for when the temperature is changing and you only have one phase of matter. The flat segments are when you have 2 phases of matter and a phase change is happening. So you have one flat segment at the melting point, one flat segment at the boiling point. Let's work some problems here. I want you to look at the formulas we're going to use for the problems. Q equals Cm delta T is the one that we've been using in this unit, but Q equals mH is another useful formula. Now that we have those flat segments of the temperature change graph and the phase change, you're going to need that. And I listed the important values for water. These are all found in your reference tables. Please notice that ice, water, and steam each has their own specific heat value, so make sure you know which phase of matter you have when you work a problem. And there are 2 heat values for water. There's a heat of fusion value, which is what happens when ice melts to liquid water, and there's a heat of vaporization value when water boils to become steam. So again, make sure you know which phase of matter you're dealing with when you work these problems. Alright, here's the first example. The heat of fusion of water is 334 joules per gram. That's just from your reference table. How many grams of ice at 0 will melt if 2,250 joules of heat are added? Alright, so the first decision is how do you know which one of those 2 formulas to use? I always say look at the temperature. You have a 0 degrees temperature here, but you don't have a second temperature. So if the temperature is not changing, you cannot use Q equals Cm delta T because you don't have a delta T. So we know we're going to have to use our new formula, Q equals M times H. Now we're just going to plug in. The 2,250 joules is the heat, and the heat of fusion is the 334 joules per gram number. We're going to plug in those values in the appropriate place. Mass is our unknown. Now, to solve for mass, we need to get the m on a side by itself. So I've rearranged here. You're going to divide both sides by 334 joules per gram. You have some units that will cancel. Joules on top cancels with joules on bottom. And when you divide 2,250 by 334 in your calculator, you get a mass of 6.74 grams. And that's the answer for this first one. Here's another one. We need to figure out how much heat in kilojoules is absorbed. When we have water at 100 degrees, they give us the pressure. And I don't remember seeing pressure in a formula. So I'm thinking that could be some extra information. And we're converting it to steam at 100 degrees Celsius. Now remember the deal with the temperature. We have two temperatures here, but they're both 100 degrees Celsius. So if I did a delta T, or a change in temperature, that wouldn't work. I would get a temperature change of 0, and I would get a heat of 0. Well, that's weird because you know you have to add heat to make water become steam. So again, I'm going to use the new formula, Q equals mH. I'm going to substitute in the 24.8 grams is the mass of the liquid water, and that gives you the standard enthalpy of vaporization for the water. That's the H value. You've got some units that will cancel out here, the grams with the grams. You're going to multiply everything side by side there, and you're going to get a really big answer. It's 56,048 joules. Remember, this question wanted the answer in kilojoules, so you're going to have to do a quick unit conversion. Remember, the prefix kilo means 1,000. So I'm going to set up a factor label problem to convert joules to kilojoules, and I'll get 56 kilojoules as my final answer. And finally, how much heat is absorbed when 6.5 grams of ice at negative 17 degrees warms up to 0 degrees? Now here I have those two different temperatures. So I think for this problem I should be able to use Q equals Cm delta T. So let's get ready to substitute values. What is the specific heat here that I want to use? This was the warning I gave you earlier. I have ice at negative 17 degrees. That's a really cold temperature, so I definitely have solid ice. If you look in the reference tables, the specific heat of ice is not the 4.18 number that we typically use for water. It's the other one, 2.05 joules per gram degrees Celsius. The mass of the ice is 6.5 grams. And for delta T, remember delta is final minus initial. So I plugged in 0 minus negative 17 degrees Celsius. Let the units cancel out, grams with grams, and degrees Celsius with degrees Celsius. When you multiply all of that straight across, you're going to get an answer in joules, and that's going to be 227 joules. I did a little bit of rounding there, so your calculator will give you the decimal answer and you do the rounding. So I've worked a problem with the new formula. I've shown you when you need the new formula, Q equals mH, and when you need the regular thermochemistry formula, Q equals Cm delta T. Now you should be able to work heat problems where you change the phase of matter as you work through the problem. Good luck with those.